All right, in problem number 5 in the section 11.3 worksheet, we're told that the carnival game known as a strength tester or a strongman game involves using a large hammer or mallet to strike a lever and ring the bell at the top of the tower. Okay, so I've included over here a poorly drawn rendition of what we're seeing here. So we have our mallet, it's going to come down and strike, and this ball is going to go up to some height that will depend on the force we exert with the mallet. Now, of course, our goal, right, is to get the ball to go up and ding the bell. That's how we're going to win a prize. Okay, so now the problem goes on to say that the force needed to ring the bell is the product of the mass of the mallet used in the acceleration given the mallet by the person swinging it. In other words, force equals mass times acceleration. Okay, and I've just abbreviated that formula here. F equals m times a. Now, part A says, if a constant force is needed to ring the bell, how are mass and acceleration related, directly or inversely? Okay, so here in this formula, what we're saying is that the force required, the F, is some fixed value. Say it requires, 100 pounds of force to get the ball to go up and ding the bell. Okay, so what does that imply about the mass and the acceleration? Well, what it's telling us, right, is that the product of these two things is going to be constant, right? Constant product, that's telling us, okay, that's inverse variation. Okay, so since here the product of the variables is always the same, m and a vary inversely. Okay, so one way to think about this is to say something like, all right, if this part F is fixed, okay, and let's say I have a large mallet, and that then requires not a huge amount of acceleration. Okay, well, if I can't change the left side, right, but let's say I can change the mass, and let's say I give someone a really, really teeny mallet, right, so the mass is really small, right, if they're going to achieve that same required force to ding the bell, that means their acceleration is going to have to be big here, right? So here we can say as the mass is, say, going up, the acceleration is going to have to go down, and vice versa. If I decrease the mass, then the acceleration is going to have to go up. Okay, so that is the essence of inverse variation. All right, great. Now on to part B. It says, if someone is given a mallet twice the size and mass of a typical mallet, what happens to the acceleration needed to ring the bell? Okay, so let's first start here with just a little numerical example to get a little bit better of a feel of this. Let's say, again, there's 100 pounds of force required to ding the bell. And let's say the mass is 25. That would then force the acceleration to be 4. Okay, so what I'm going to do now is I'm going to double the mass. Okay, so if I double, so multiply here by 2, that's going to give me a mass of 50. And on the left, I can't change that number, right? That's the required force, say 100 pounds to ding the bell. So then what must happen to the acceleration? Well, it's going to have to go down from 4 to 2. Or put another way, we're going to have to divide the acceleration by 2. Okay, so the punchline here is that if we double m, so if m is doubled, then the acceleration will have to respond by being halved. And a is halved. Okay? Alright, so that settles the problem. But before we move on to C, I do want to explain something real quickly that will help us in a problem like part C, and we'll also see the same thing in problem 6. another slightly different way to see this is to go back to just this relationship F equals ma. Okay, so m times a. And what we're doing here, right, is we are doubling the mass. Okay, so I'm going to put a 2 in front of the m, right? So if I double the mass, what must I do to the acceleration so the left-hand side will come out to be that same constant value, say the 100 pounds, right? Well, just as we saw here, if I double m, that means I'm then going to have to take 1/2 of the acceleration. So these two effects, the doubling and taking the half, in essence cancel out, leaving us with that same constant force on the left. But again, this is just another way to see, okay, doubling m will have the acceleration, all right? Now with that in mind, let's look at part C. It says if someone is given a mallet 1/3 the size and mass of a typical mallet, what happens to the acceleration needed to ring the bell? Well, to answer that, I'm again just going to look at this relationship, F equals ma. And what we know from up here, right, is look, if I'm going to make the mass smaller, in this case, a mallet the size that's 1/3 the size of the original, right, then the acceleration is going to have to go up. By how much? Well, if I take 1/3 of m, then in response, the acceleration, to cancel that out, will have to triple. Okay, so here the punchline is that the acceleration will be tripled. Okay, that's going to do it for this problem.